Hello and welcome, dear students. Today we will discuss the topic oceanic waves and the mechanisms. Oceanography is the study of the physical, chemical, biological and geological characteristics of the world's oceans. Within this broad field, coastal zones are especially important because they support most marine ecosystems and provide vital resources and services to the human society. The oceanic surfaces in these regions is rarely calm. Instead, it is in constant motion, shaped by dynamic processes. Among these, tides, waves and currents are the primary factors controlling surface water movement. Each plays a crucial role in shaping coastal landscapes, influencing oceanic circulation. Among these processes, waves are the most common and continuously active movements on the oceanic surface. A wave can be simply defined as a disturbance or rhythmic rise and fall of the water surface because winds blow over the oceans almost constantly. Waves are the widespread and remain active throughout the year. Waves are especially important in oceanographic studies because they influence many natural and human related processes. They play a key role in coastal erosion, sediment transport, marine habitats, nutrient mixing and navigation safety. Understanding wave behavior is also essential in fields such as marine biology, marine geology, fisheries science and marine engineering. This knowledge helps scientists and engineers design coastal structure, protect shorelines, manage fisheries and better understand how marine environments respond to natural forces. Now, cause of oceanic waves. Oceanic waves form when energy is transferred through a fluid, creating disturbance in the water. In marine environments, this energy comes from both natural as well as human induced forces. Waves are not confined to the ocean surface. They can also develop in boundaries between different fluids or within layers of the ocean itself. Because both air and seawater behaves as fluids, wave motion can occur at their interface as well as within the ocean interior. Ocean waves vary widely in size, energy, ranging from small ripples to calm water to extremely large and destructive waves, such as tsunamis. Wind is the most common and effective generator of oceanic waves, as friction between moving air and the sea's surface transfers energy to the water. Overall, the fluid nature of both air and ocean allows waves to form at their interfaces and within them. Waves at the air-water interface. Oceanic waves form where air meets the ocean surface because air and water have different densities. Wind blowing over the sea surface creates friction, which disturbs the water and generates waves. This process occurs because the lighter air moves over the denser water, making the boundary between them unstable when wind energy is applied. Initially, small ripples form which can grow into a larger waves if the wind is strong and persistent. The height and the strength of wind generated waves depends on three main factors. Wind speed means how fast the wind blows, wind duration, how long it blows, and fetch, the distance over which the wind acts. These surface waves are responsible for shaping beaches, affecting navigation, and influencing coastal processes. Second, waves at the ear-ear interface. Waves can also develop within the atmosphere, where masses of air with different densities interact, and especially when cold, dense air pushes into the warmer regions which form in the atmosphere. These frequently take the appearance of bands of rippled clouds. They are reminder that the atmosphere behaves as a fluid not too unlike the oceans. Third, waves at the water-water interface. They are also called internal waves. Internal waves form below the ocean surface along boundaries between water layers of different densities, normally around the pycnocline, a zone where the density of the water changes rapidly. These waves can be much larger than surface waves, sometimes over 100-meter high. These waves are generated by tides, turbidity currents, storms, or even passing ships. Turbidity currents are underwater landslides made of water mixed with mud, sand, clay, and other sediments. These currents move rapidly downslope on the seafloor. When they move, they displace large amount of water, which can create waves at the surface. These waves are powerful enough to affect submarine navigation, sometimes appear at the surface as long, parallel silics of floating debris can be detected from space. Due to their large size, internal waves show that the interior of the ocean is not static. Fourth one, waves caused by mass movements. These are waves generated by sudden input of mass into the sea, such as from landslides, collapsing cliffs, or large icebergs falling from glaciers. While localized, these waves can be powerful and dangerous along steep coastlines. Fifth one, waves form seafloor disturbance. These are also called tsunamis. The earthquakes or a volcanic eruption deep beneath the ocean causes tsunamis and can propel massive amounts of water upward in an instant. If the blast is big enough that water rushes out as a tsunami, they stretch for miles and race across oceans at incredible speed, barely slowing down as they go. Tsunamis don't happen every day, but when they do, they are a real threat to anyone living near the coast. As the waves hit shallow water, they pile up fast, growing taller and pushing further inland. That is when they can really tear things apart and leave a long trail of damage behind. Sixth one, tides as waves. The gravitational pull of the sun and moon on the Earth's oceans creates a long, slow moving waves known as tides. Although tides are not like regular wind waves, they are still waves because They involve the movement of water due to extensional forces. Example, during a full moon and a new moon, high tides became higher and low tides became lower, because the gravitational pull of the moon and sun combine. Tides are the longest waves in oceanic system. Human generated waves. Humans don't just watch the ocean, they shape it. Two big ships can throw off waves strong enough to rock smaller boats nearby, sometimes even knocking them off course or making them wobble. In places where the water is shallow or close to the shore, these waves can add up, slowly eating away at the shoreline. And it is not just a problem for people. Dolphins and other marine animals sometimes hitch a ride of these waves, saving themselves a bit of effort. Now and then, humans kick up even bigger waves. Massive events like underwater nuclear or missile tests dump and sudden jolts of energy into the ocean. These waves usually stay close to where they started, but they are a good reminder that when people mess with the ocean, the effects can be dramatic. They tell a bigger story that includes the constant push and pull of natural forces, but also the ripple effects of everything people do on the water. Understanding how waves move. Waves are the best thought of as energy in motion. They transmit energy from one location to another within a material of the medium, merely vibrating or oscillating in small repeating motions. Such motions are back and forth or up and down movements through which energy passes from particle to particle so that a wave can travel. When you tap a table, the impact creates vibration that move through the table as waves. Waves can move and transfer energy in different ways. One of the most common type is the simple progressive wave. These waves move forward smoothly without braking, and their motion repeats in a regular pattern. Progressive waves can be longitudinal, transverse, or orbital, depending on how particles in a medium move as wave passes. Oceanic waves are unique because they show a combination of both longitudinal and transverse motions. As a result, the water particles move in circular orbits. These waves travel along the interface between air and water, which is why they are also called interface waves. In orbital waves, particles move forward and backward, longitudinal component. Particles also move up and down, transverse component. Combined, these motions create a circular path. This circular movement is what we observe as the familiar rising and falling of ocean. Wave terminology. As an idealized wave passes a permanent marker like a pier pilling, you notice this repeating pattern of crests coming up and troughs going down. The crest turns out to be the highest spot on a wave. A trough is the lowest part you can see. Right in the middle, between a crest and a trough, lies a still water level. This state is also called the zero energy level. That is, the level matches the calm surface water would have without any waves disturbing things. The wave height designated is the vertical distance between crust and a trough. The horizontal distance between any two corresponding points on successive waveform, such as from crust to crust or from trough to trough, is the wavelength. Wave steepness is equal to wave height by wavelength. If the wave steepness exceeds 1/7, the wave breaks or spills forward because of the wave is too steep to support itself. This ratio also indicates the maximum height of the wave. The time it takes one full wave, one wavelength to pass a fixed position like pier piling is the wave period. Typical wave periods range between 6 and 16 seconds. The frequency, also designated by f, is defined as the number of crusts passing a fixed point, fixed location per unit of time, and is the inverse of the period. Frequency is equal to 1 by period. Most of the waves present on the oceanic surfaces are wind generated waves. As wind velocity increases, wavelength, period and height increases, but only if wind during and fetch are sufficient. Motion of water particles. The fundamental concept behind oceanic wave creation is the movement of water particles. As a wave travels across the oceanic surface, the water itself does not progress forward. Rather, the water particles follow small circular paths called orbits. These orbits are largest at the sea surface with a diameter approximately equal to the wavelength. When the wave reaches a crust, the water particles moves forward in the same direction as the wave energy. Descending below the sea surface, the diameter of these circular motions diminishes progressively. This means the wave energy decreases with depth. At the trough, the water particles travel opposite to the wave movement. Also, during the lower half of the circular path, the particles move more slowly compared to the upper half near the crust. Deep water waves. The characteristics of waves differ with reference to deep and shallow water depths of the water, controls their speed, shape and motion. To understand this better, oceanographers classify waves based on the relationship between the water depth d and the wavelength L. There are three types of waves defined by water depth: deep water waves, where d is equal to or greater than 1/2 of wavelength L. Second one is the transitional wave or intermediate water wave, where d is greater than 1/20th and less than 1/2 of wavelength L. Third one is shallow water wave, where d is less than or equal to 1/20th of L. In deep waters, the water depth d is greater than half of the wavelength L. All wind generated oceanic waves move across the oceans or all deep oceanic waves. In shallow water waves, waves in which the water depth d is less than 1/20th of the wavelength, that is d is less than L/20, are classified as shallow water waves. As waves enter the shallow water zone, they become taller and slow down and eventually be breaking on the seashore. Transitional waves are waves that behave partly like deep water waves and partly like shallow water waves. This happens when The water depth is neither very deep nor very shallow. The speed of the wave depends on different factors. In deep waters, the speed depends mainly on the wavelength, while in shallower water, the speed depends mainly on the water depth. Since transitional waves fall in between these two conditions, their speed is controlled by both the water depth and the wavelength. Thus, transitional waves are a mix of both wave types, showing combined characteristics as they move from deeper to shallower areas. Wind and waves are closely connected. When winds blow over the surface of the ocean, it transfers energy to the water, creating waves. To help sailors understand sea conditions, the Beaufort scale was created in 1805 by the Admiral Sir Francis Beaufort. It classifies wind speed and the type of waves it produces. For example, Beaufort scale 0 means the sea is calm and smooth like a mirror. Scale 6 means strong winds creating large waves with a white foam crust, and scale 12 represents hurricane conditions with extremely high and dangerous waves at beaches. Waves are the main force shaping the shoreline. They move sand from one place to another place, creating currents along the coast called longshore currents. Stirring up sand through turbulence and slowly changing the shape of the beach over time, waves rarely hit the shore straight on. They usually come at an angle, which causes sand to move sideways along the coast, constantly reshaping the beach. Now, let us discuss breaking of waves. When ocean waves move in deep water, they travel smoothly without changing much in shape, but as they get close to the shore, water becomes shallower. This change in depth affects the wave behavior. The bottom part of the wave begins to touch the sea floor and experience friction. Because of this friction, the lower part of the wave slows down, but the upper part of the wave continues moving faster. This difference in speed causes wave to rise higher, become steeper, and eventually lose its balance. This is why waves break near shore. As waves break, wave height increases, the water is pushed upwards, wavelength decreases, the wave slows down and becomes shorter. Wave steepness increases, the wave becomes sharper and more vertical. When a wave finally collapses or falls forward, it releases a huge amount of energy. This energy is called surf energy. To understand how powerful breaking waves can be, a wave only 1.2 meter high can release energy equal to 50 million horsepower when it breaks. The area near the beach where wave keeps breaking again and again called the surf zone. This is where you see a lot of foamy water, rolling waves and strong currents. It is the zone where most beach activities and surf action takes place. Sippling breakers are gentle waves that form when the seafloor rises slowly towards the shore. Because the slope is smooth and gradual, the wave does not crash suddenly. Instead, the top of the wave slowly becomes unstable and soft white foam gently spills down the front. These waves break for a longer time and look calm and rolling. They are the safest and softest type of breaking waves and are commonly seen on wide, gently sloping beaches. Plunging breakers occur when the sea floor becomes very steep or when the water depth changes suddenly, such as near reefs or sandbars. As the wave moves into this steep area, the bottom of the wave slows down quickly, but the top keeps moving faster. This makes crust rise sharply, curl forward, and then fall or plunge down with great force. These waves release a lot of energy all at once, which is why they can be dangerous. Plunging breakers create the famous tube or barrel shape seen in surfing. Surging breakers form on a very steep beaches where waves do not get enough time or space to rise, curl and break normally. Instead of forming a crust or spilling like other waves, these waves rush straight up and shore as a fast moving wall of water. They look powerful and sudden because the water moves quickly up and then forcefully back down the slope. The backwash can be very strong and can pull people, stones and objects towards the sea. This makes surging breakers dangerous, especially on rock coastlines. They occur because the steep seabed reflects most of the waves energy upward instead of letting the wave break gently. Collapsing breaker. They are combination of both plunging and surging waves. In these waves, the crust starts to form as if it is going to plunge, but it never fully turns into a tube. Instead, the lower part of the wave collapses and creates a burst of foam. This type of breaker usually occurs where the beach slope changes suddenly from gentle to steep, causing the wave shape to become unstable. Rogue waves are extremely large and unexpected ocean waves that can appear suddenly. Even when the sea looks calm, these waves are also known as freak waves, monster waves or killer waves because they can be 2 or 3 times taller than the surrounding waves and are powerful enough to damage or even overturn large ships. Rogue waves usually form when strong winds, fast moving oceanic currents or several wave systems combine together and reinforce each other, creating one giant wave. A storm surge is when sea level suddenly rises during a storm. This happens because strong winds push water towards the shore and low air pressure lets the water rise even higher. Strong surge can cause flooding along the coast and they become even more dangerous if they occur during high tide. The waves and water form a storm surge can travel far inland, damaging homes, roads and other coastal areas. Coastal areas often experience severe flooding during cyclones because of storm surge. A sash is a type of standing wave that forms in a closed or partially closed water body such as lakes, bay or harbor. In a sash, the water moves backwards and forth like a seesaw. These waves usually have a very long wavelength, so they are hard to notice within the naked eye. Sashes are often caused by strong winds, changes in air pressure or even tsunamis. That was all about today's lecture. Hope you have enjoyed it. Thank you.